Good morning, everybody. My name is Mairo Moreira. I'm from Federal University of Viçosa, Brazil, and I will present this paper titled Genetic Algorithm for Tardiness Minimization in Flowshop with Blocking. This paper also was written by Tiago Oliveira Januário and José Elias Cláudio Arroyo. In our outlines, we have the definition of the Flowshop scheduling problem, the objective of this paper, the methodology used, including the implemented genetic algorithm, computational results, conclusions, and acknowledgements at the end of the presentation. So about the problem bordered in this paper, the Flowshop scheduling problem, we can define in this way a set of n jobs that must be processed on the machines in such a way that the total tardiness is minimized. So the total tardiness is given by this formula, that is the sum of each tardiness of each job, where the Ti is the tardiness of a job I, given by this formula, Ci is the completion time of the job I, and Di the due date of the job I. So in this work, we consider the permutation Flowshop scheduling problem with blocking in process, a constraint. So in this problem, there are not buffers between successive machines, or in other words, it is not allowed an intermediate queue of jobs waiting the system for their next operations. So as you can see in this example that has 2 machines and 4 jobs, we can see not only the characteristic of the problem, but also the constraints bordered in this paper. So we have here that all jobs must be processed in the same order in each machine. And in this case, the job 1 finished its processing on machine 1. It must remain in machine 1 until the machine 2 started this processing. The same occurrence we can see with the job 3. So there are not intermediate storage spaces between 2 successive machines. So our aim, our objective with this paper is propose an adaptation of a genetic algorithm, the GA, for the permutation Flowshop problem with blocking in process in order to minimize the total tardiness of jobs. To do this, we use different strategies such as local search, diversification of the population, and intensification based on the path relinking technique, a post-optimization procedure. So here you can see the phases of the genetic algorithm proposed by us. So first of all, we have the population of solutions, and using some technique of selection, we selected some parent solutions in order to be recombined. And using a probability of recombination, a probability of crossover, we recombine the solutions, generating offspring solutions. So with this offspring solutions, we applied a mutation operator with another probability. And of course, we applied a local search procedure in order to improve the solutions of the new population, the recombined population, using another probability. And if a stopping criteria is not reached, we goes on with the execution of the algorithm, trying to apply a diversification criteria, a diversification of the population. And if this stopping criteria is reached, we apply the intensification procedure using the path relinking technique. And in the end, we return the best solution obtained in all generations of the genetic algorithm. So about our implementation of the genetic algorithm, we use in such a way to represent the solution an array of numbers from 1 to n that represents the permutation of jobs, as you can see in this example. In order to generate the initial population of the solutions, 50% of the solutions are generated using an EAH heuristic adapted in order to generate more than one solution. And the other 50% of solutions are generated randomly. So in this paper, we use the population size equals to 20 solutions. In the selection phase, we use the tournament selection technique that consists in select a number of solutions randomly and select the best among them. So in this paper, we selected 3 solutions of the population, and we take the best among them, the best solution among these 3 solutions selected. The recommendation phases, we tested 2 types of crossover, the OP crossover and the SJOX crossover. So about the first one, we implemented it this way. We selected a cut point in the job sequence, yeah, as you can see in this example, and all the jobs before this cut point of parent 1 and parent 2 are assigned to offspring 1 and offspring 2 respectively, and the other jobs that must be filled in offspring 1 and offspring 2 are completed with the missing jobs of the parent 2 and parent 1 respectively. And about the SJOX crossover, first of all, we identify the jobs that is in the same position that corresponds similar in parent 1 and parent 2. So as you can see, 3, 4, 2, and 1. And the other jobs that is inserted in offspring 1 and offspring 2, we use in the same way as we use in one-point crossover after we apply a cut point, etc. So in this implementation, the SJOX crossover presents the best results, and we applied the crossover with 30% of probability. The mutation operator, we use the insertion operator, as you can see in this picture, yeah, and we use this operator with 5% of probability. The local search procedure, a procedure that is used to improve the offspring solutions, is based on the insertion neighborhood. So we try to insert all the jobs in all positions in the job sequence. And we also use the idea of the first improving, that consists in replace a current solution by the first neighbor solution, which improves the objective function or the total tardiness value. So in this paper, we applied this local search procedure with 80% of probability. About the diversification of the population, this procedure is used in order to avoid the homogeneous convergence of the algorithm. So we apply this procedure after 20 iterations with no improvement of the best solution. And the restart procedure consists in keep 20% of the best solutions, the elite solutions of the population, to generate another 20% of the solutions, making mutation in the elite solutions, generate 30% of solutions by the NIH heuristic, and the other solutions are randomly generated. The path relinking technique, the post-optimization technique, consists in explore the path between an orange solution and a guide solution. So we explore this path, making swap movements with the job sequence in order to find the solutions more similar to guide solution and less similar to orange solution. So in order to continue the trajectory, we select the solution which has the best value of the total tardiness. So in this paper, we applied the path relink technique with from 20% of the population, the elite solutions, and 20% of the population, random solutions selected to this population that not belongs to the first set that we use, the elite solutions. So the test problems used in this paper were generated according to Taillard. The processing times are in this range, the due dates in this range, where P is given by this formula. And we use 4 scenarios of due date in such a way that A is the tardiness factor and B is the range of the due dates. We use this size of problems, and for each combination of number of jobs and number of machines, 10 different matrices of processing times were generated. As I said, we have 4 scenarios of due dates, and the total of the test problem were 480 problems. And of course, our stopping criteria, we use the CPU times equals to number of jobs squared plus number of machines milliseconds. As you can see in these examples, for a schedule with 20 jobs and 20 machines, we waste 80 seconds to solve the problem. We implemented 3 versions of genetic algorithm: the basic one, the genetic algorithm with a local search procedure, and the third version, the genetic algorithm with local search procedure and a path linking post-optimization. So as you can see in this graphic, the third version of the genetic algorithm outperforms the other versions in most of the problems, as you can see in this graph. So here we have the number of problems, and here we have the value of the total tardiness. So the third version outperforms the other versions. And the results obtained by this proposed GA are compared with the results of the grasp meta-heuristic proposed by Ronconi and Enriquez. This meta-heuristic is so famous and so important in this kind of problem, and it has one of the best results for the total tardiness value in order to minimize the total tardiness value. And the GA efficiency is evaluated by the relative improvement percentage given by this formula, where T is the value of the total tardiness obtained by each algorithm. So in this table, we have the average of improvement percentage obtained by the GA with local search and the GA with local search and path relinking. So as you can see, the average of the improvement by the GA2 was 1.78%, and the GA3 4.90%. So we have another graphic. As you can see, the GA3 outperforms the GA2 and the grasp meta-heuristics in most of the problems presented above. Conclusions. In this work, the GA was proposed for the permutation flowchart scheduling with blocking process. This GA uses some strategies such as local search, diversification of the population, and intensification procedure based on the path relinking, a post-optimization procedure. And these strategies contributed greatly for the good performance of the algorithm. Our proposed algorithm outperforms the grasp meta-heuristic. And for a total of 408 problems, the GA3 obtained an average of improvement of 4.90% with relation to grasp meta-heuristic. First, so in the end, I'd like to thank the Arthur Bernardes Foundation and CNPq for all the help in the development of this paper. Thank you very much. And in case of questions, please send an email to any of authors here. So at least but not last. Thank you very much. Muchas gracias. Muito obrigado.